What's up everyone, and thank you for choosing to learn with LAM. Today we're going to be taking a look at enthalpy of formation and seeing how it can be used in conjunction with Hess's Law. If you're not super familiar with Hess's Law, you can check out the Hess's Law tutorial. The link is in the description below. So first things first, molar enthalpy of formation is the change in enthalpy when 1 mole of a compound is formed directly from its elements in their most stable state at SATP. So for example, hydrogen gas plus half oxygen gas makes liquid water. This is the formation equation for liquid water, and it has a molar enthalpy of formation of negative 285.8 kilojoules per mole. Now, notice that formation is from elements in their most stable state. So, for example, oxygen gas is not the only form of oxygen. You could have ozone or just atomic oxygen, but the most stable state of oxygen at SATP is gaseous O2. Also, molar enthalpy of formation is about forming 1 mole of the compound. So because this is the formation of water, our molar enthalpy is per mole of water. And on a related note, because we're mostly focused on creating 1 mole of our compound, it's not uncommon to see fractions on the reactant side of our equation. It just depends on what you're trying to create. Anyway, molar enthalpy of formation is very useful in conjunction with Hess's Law, as it allows us to determine the enthalpy of any reaction without having to perform it, as long as we know the starting reactants and the end products. Recall that Hess's Law states that regardless of the pathway, as long as the reactants and products are the same, the enthalpy change will be the same. Now, the equation we're going to use here looks complicated, but it's pretty easy to apply. It goes delta HR equals sigma N times delta H naught F products minus sigma N delta H naught F reactants. Now, sigma means sum of, and I'll show you how to utilize that in a minute. N is for moles as usual, and delta H naught F is molar enthalpy of formation, and we have 1 for products and 1 for reactants. Like I said, I promise it's easier than it looks, so let's jump into a practice problem. What is the enthalpy of combustion of 1 mole of methane? Well, first off, we need a balanced chemical equation. And after that, let me show you how we're going to set up our problem. Let's rewrite our equation, just so we can see directly what's happening here. Alright, so the first thing we're looking for is information about our products. They're over here. So I'm going to use the coefficient as the mole here, so 1 mole of carbon dioxide. And then we'll look up the molar enthalpy of formation of carbon dioxide in the table provided to you by your teacher or in your textbook, and it's negative 393.2 kilojoules per mole. Just for clarity, this means that the formation of 1 mole of carbon dioxide releases 393.2 kilojoules. Now, remember that sigma means sum of, so I need to add the same information about water. So we're adding 2 moles times the molar enthalpy of formation of water vapor, which we're looking up and is negative 241.9 kilojoules per mole. So that's it for my products, and now I have to subtract my reactants, which are these guys here. Here we go again. We've got 1 mole of methane, so 1 mole, and the table says molar enthalpy of formation for methane is negative 74.6 kilojoules per mole. Again, sigma means sum of, so plus 2 moles of oxygen gas, so 2 moles down here. And here's the thing we need to remember about oxygen gas. It is the most stable form of elemental oxygen at SATP, so its molar enthalpy of formation is 0. You can look it up in a table, but it likely won't be listed, so don't be thrown off. Now we just have to cancel out our units, and we're left with negative 877.1 kilojoules, which comes from my products, and we subtract negative 74.6 kilojoules, which comes from our reactants. And that gives us a total enthalpy of negative 802.5 kilojoules for the combustion of 1 mole of methane. Now, if you're satisfied with just the mathematical approach, then there you have it. We have our answer. But if you need some deeper understanding, consider this. What our equation is really telling us is that creating the products we want releases 877.1 kilojoules of energy. It also tells us that creating our reactants releases 74.6 kilojoules, but we're not creating our reactants, we're breaking them down. So that enthalpy is actually positive 74.6 kilojoules. It's the reason we're subtracting the enthalpy of formation of the reactants, because it flips the sign. Now, for the record, that's not how reactions actually work, where reactants are broken down to their elements before creating the products. But remember, according to Hess's law, it doesn't matter what the process is, so long as the reactants and the products are the same. So, if we look at this graph here, we can see that the change in enthalpy from start to finish is negative 802.5 kilojoules. And that's that. As always, if you have any questions or if you have any topics you want me to cover, just leave them in the comments below. Good job, everyone. If you find that you need a little extra help, please feel free to check out my other videos for tips and tricks on how to succeed in school. And as always, thanks for learning with LAM.